before, where we were talking about how we can draw these polynomial functions, graphs. So we had talked about symmetry, you know, with terms of y-axis or the origin, or if it's a quadratic function, it has its own symmetry. We had talked about the behavior at x-intercept, so that way we know if our graph will be crossing the x-axis or just touching the axis but not crossing it. And the other important thing we had talked about is how the leading coefficient can actually help us determine what the arms of our graph will be doing, you know, what direction they will be heading in. So we were basically putting all of this information together to try and see, oops, not this guy, to try and see what kind of function we would have in this case. So we did come up with an even function over here. We had -3 x to the 4th plus 15. So as you can see, this is an even function. Our next step was finding the x-intercept. So do you know how you would find the x-intercepts here, so we can talk about the behavior of our function at the x-intercepts? What process would we have to do to find the x-intercept for this function? Okay, so Oliver, you are talking about using the quadratic form. So what would we do for the quadratic form? And what other method can we use instead of the quadratic form if we wanted to use something else? Come on, think about it. It's not that hard. How do you normally find your x-intercepts?
The P over B thing? Oh wait, no, that was something else.
And this may mean you would have to go back to chapter 1 if you cannot remember how to find x.
Can you replace y with 0?
Exactly, yeah, you just replace your y variable with 0, set your equation equal to 0, and you should be able to come up with that. So Oliver, what happens when you're talking about quadratic form? I don't know if you were talking about in terms of, you know, where we replace the x to the 4th power with u to the 2nd power, which is what we had talked about in chapter 1, where we had seen how we can take equations and rewrite them in the quadratic form, and then you can solve them. So by rewriting this in the quadratic form means then you will be able to use the quadratic formula. So that's definitely a possibility. So I would say go with whichever method you are most comfortable with. And this one actually being a fairly simple example, that's fine, not a problem, Oliver. So yeah, whichever method you are comfortable with, go with that. But basically the idea is find out what your x-intercepts are going to be. So for this guy, if we take our -3 x to the 4th plus 15 and set it equal to 0, then that can help us come up with, you know, what our x-intercepts are going to be. So solve this like an equation. You can start by moving that 15 to the other side. We end up with -3 x to the 4th equals -15. Then of course we're trying to get x by itself. So divide both sides by -3. And let's see, that will end up giving us x to the 4th equals negative and negative will become positive. 3 goes into 15 5 times. So what will we do going forward to get the x by itself? What process would you have to use?
The square root?
The square root. Okay, let me see. Yeah, so since this is actually raised to the fourth power, you would actually have to use the fourth root. So Nathan, you were talking about, do we need to do the square root twice? Doing the square root twice, I guess technically would still mean the same thing as taking the fourth root. So yes, because just like cube root cancels out the cube and square root cancels out the square, in that same way, oops, fourth root would cancel out the fourth power. So let's take a look at that. So that means we will do fourth root of x to the fourth equals, and since fourth root is actually an even root, just like square root is, you will end up with a positive and a negative answer in this case. So your fourth root will cancel out the fourth power, leaving us behind with x, and we will have plus or minus the fourth root of 5. And just so we know where on the graph this point will be, you can find the decimal approximation for fourth root of 5. And do you know what that number will come out to be when we take the fourth root of 5? Okay, let's take a look. Yeah, it's going to be, oh, that's not what I came up with, James. Good, yeah, that's what I had, which Nathan came up with. 1.495, and of course the number keeps going. If you want to round this to 2 decimal places, that would be approximately 1.5. Okay, so we've got our x-intercepts. Now this is actually going to be an interesting example, because if you think about where we got these answers from, you can kind of think about it as x to the fourth, but x to the fourth was equal to number 5, right? It was not equal to the plus or minus 1.5. So typically when we talk about the behavior of our x-intercepts, usually we're talking about, are they going to cross the x-axis, or are they going to touch but not cross? So you will actually see, and oops, wrong one. You should be able to see from all of these graphs here that we are actually crossing the x-axis in all of these graphs over here. So this one actually just works a little bit differently, just the way this problem, ends up, how we end up solving it to get our x-intercept. So let's use our leading coefficient test to kind of help us see in what direction the arms of our function are headed in. So leading coefficient test, you are only looking at the leading term, which is negative 3x to the fourth. So since this is an x to the fourth polynomial, that means our n is an even number, and our coefficient is negative 3. So our coefficient, of course, is a value less than 0. So with even and negative, what do we expect from our leading coefficient test? Where are the arms of this graph headed? Yeah, very nice. They are going to go downwards, because you can think with even and negative, that's basically a parabola that's heading downwards. Yeah, very nice. Good job, guys. So that means as x goes to positive infinity, y actually goes to negative infinity. And as x goes to negative infinity, our y will also go down to negative infinity. So that automatically tells us these graphs where the arms are facing upwards obviously is not going to be our graph. So now between graphs B and C, and since this is actually an image I took last time from the example. I will not be able to expand these graphs. So which one would you have to choose looking at our symmetry, x-intercepts, and the leading coefficient test? Yeah, very nice, guys, because we know our graph has symmetry with the y-axis. Our graph, of course, has intercepts at positive and negative, approximately 1.5. And we also know our graph is headed downward. So you can see that is definitely fitting the description of this graph B over here. So just use these three different tests to kind of help you out. Now the leading coefficient test and symmetry really were the ones that helped us out over here. Behavior at the x-intercepts obviously does not follow the convention rules, but at least you get to see where your x-intercepts would be at. So you will actually have few more examples like this one in your homework. So let me go back to our 3.4 over here. And I would say, again, use these three different tests to help you out. Symmetry, the behavior at the x-intercepts, and the behavior in terms of the leading coefficient test. So let's see. So some of these examples we had talked about last time. This is, again, one of the examples. This is kind of similar to what we just looked at. And so you can see various different versions. This one is asking you to graph the function yourself. Same thing over here. Choose your graph. So use these techniques. And as always, if you need help, let me know and I can help you out with those. And then the last part in this section, we're actually talking about how to solve polynomial inequalities. So you can solve these by using the graphs of your polynomial functions, or you can solve these by finding the test points using the test point method. So just as a quick overview, when we talked about quadratic inequalities, we had talked about the test point method. So remember, that is where you find your x-intercepts or the zeros for your function. And then from each interval, you would choose a test point, plug it into your function, and see where you get a positive or a negative sign. And then some of these examples are, of course, using the graph to help us solve it. So this is your equation, x cubed minus 36x. And you can see this is greater than 0. And they're asking us to solve this by looking at the graph for this function. And this is kind of what the graph for this function ends up looking like. Let's make this guy just a little bit bigger. And then we have, what did I do? There we go. Okay, so we are given x to the third minus 36x is greater than 0. So if you think of this as being our y value, we're basically asking where is the y value going to be greater than 0. So since you already have the graph to go along with this, where do you think, over which interval will our graph be satisfied, or will our graph satisfy our inequality? So what interval would you pick for this? Okay, let's see, Abdul Aziz, you're talking about going from -6, which would be here, to 0. So that would be this interval over here. And you're then talking about going from +6 to infinity, which would be going in this direction. And Oliver, you're saying you basically agree with that answer? Okay. Anybody who thinks it should be a different interval than what Abdul Aziz has here in our chat? So where your y values are positive, so of course you can see for this part of our graph, the y value is positive. over here, of course, the y value is negative. Since, again, this part of our graph is below the x-axis, again, we know the y values will be negative. And then this portion here, again, your y values are positive. So yeah, very nice. Going from -6 to 0, all the y values are going to be positive. And then going from +6 to infinity, same thing, all the y values are going to be positive. Now be careful, because depending on what your inequality symbol is, you will know if you need to include your endpoints or you don't need to include your endpoint. So since this is just a greater than inequality, there's not that little equal to sign. That's why we are not including the -6, 0, and the 6 in our interval notation, because remember, right here at -6, your y value is equal to 0. Right here at the point 0, 0, again, our y value is equal to 0. And same thing with +6. So that's why we do not want to include these endpoints. Alrighty, so let's plug this answer in. So we are looking at -6 to 0 union, whoa, what did I do? Union +6 to infinity, and not including our endpoints. Okay, very nice. Let me see. That's fine, Oliver. So same kind of thing happening here with this example. I'm trying to keep my graph with my equation over here. So as you can see, our equation is x to the 4th plus 1,225, and then on the other side you have 74x squared. So the first thing, actually, it makes sense is to put this in the standard form, bring everything over to the left-hand side, and then you have greater than equal to 0. So you're basically just moving that 74x squared to the left-hand side. And the graph that you see over here is actually representative of this x to the 4th function over here. So this is basically our y value, and we're saying y is greater than or equal to 0. So what do you think, again, looking at this graph, what will be your interval notation that will satisfy this inequality? Let me see here. Abdul Aziz, you've got -∞ to -7. Then you are going from -5 to 5. And you're going from 7 to +∞. And then looks like James, you have the same interval notation. And so yeah, you can see we are right here at -7. This is -5. This here is +5, and this is +7. Looks like Nathan, you also have the same interval. Okay, so you're basically saying from -∞ to -7, which will be this portion over here, our values are positive. And yeah, you can see right here, y values are going to be positive. Then it dips down below the x-axis, so that portion doesn't count. And then between -5 and +5, again, we can see all of our y values will be positive again. And then it goes back to being positive once we hit 7. And then we're working our way towards +∞. And again, y values are greater than 0. Now in this case, since our inequality is greater than and equal to, that means at these points, our y value is going to be equal to 0, and we need to include that because of our inequality. So that's why at every one of these integers, you are going to be using a bracket to show that you are including these endpoints. Of course, infinity and negative infinity always use parentheses, and then you're putting a union symbol between all three of these intervals. So yeah, very nice. You can see once the graph is given to you, it really becomes fairly easy to try and see how your inequalities would be solved. So let's check this answer over here. Now I do want to point out that, you know, if we were doing this not as a remote class, but a face-to-face class, then, you know, we would actually need to come up with these graphs. They would not be given to you. So again, those techniques we learned about graphing polynomial functions, we would need to use those in here. So going from negative infinity to -7, including that answer, then union -5 to 5, a union again, and then from 7 to infinity. So at each endpoint, we are including them. Let's check our answer here. And there you go. Okay, so obviously my MATLAB is making it a little bit easier for us because they're giving us the graphs and we don't have to come up with the graphs on our own. But that was the last part we needed to talk about from section 3.4, is how you could use the graphs or the test point method to solve these polynomial inequalities. So again, guys, you can look at the video lecture if you want to see how the test point method would work. So again, if you have not seen the video lecture, go take a look at it. And the last section we have to talk about in this chapter is section 3.5. And as you can see, this is getting into rational functions. And rational functions basically means you are going to have a numerator and a denominator. So they look like rational numbers in the form of a over b. The only difference is our numerator and denominator will have polynomial functions in those positions. So it's basically a ratio of polynomial functions, and you can see your two examples over here of what a rational function would look like. So basically, polynomial on the top, polynomial on the bottom, and since we do have that fraction format over here, we want to make sure that our denominator will never be equal to 0, because anything divided by 0 is undefined, and that will be true for these rational functions. So because we know our denominator cannot be equal to 0, any of the x value that will make our denominator 0, you actually exclude that from the domain of your function. So let's take a look at how we can find these domains. You know what, actually, let's take a look at this guy here. So our function is given to us as -2 over x squared minus 6x. So to find the domain for this function, you literally just take the expression on the denominator and set it equal to 0. So you will be taking x squared minus 64 and you set it equal to 0. You can use the square root property to solve this. You can use factoring to solve this, or whatever you are comfortable with. So can you tell me what answers you will get for x when you solve this equation? Okay, Nathan, very good. Positive and negative 8. And looks like James, Lowell, Trey. All right, very nice. Robert, yeah. So you can start by, you know, just moving that 64 to the other side. Yeah, Javier, Oliver. Good. Then using your square root property, just like we did with that x to the 4th function, take a square root on both sides, which will give you one positive, one negative root. So you get x equals positive or negative 8. If you wanted to use factoring, you can use factoring to solve this guy also. So this actually is a difference of squares. So this factors into x minus 8 and x plus 8. If you take each factor and set it equal to 0, you will get the exact same answers you got from the square root property. So x equals 8 or x equals negative 8. So remember, the idea is both of these numbers are going to make our denominator 0. So if we do a quick check with using these two numbers, we'll start with positive 8 first. You can see we'll end up with negative 16 over 64 minus 64, which is of course negative 16 divided by 0. And like I said, divided by 0 we know is undefined. So that means our x cannot be equal to 8. And you will see a similar answer coming from negative 8 if we put that into our function, because now we will end up with positive 16 over 64 minus 64, which is again 16 divided by 0, which we know is undefined. So we are saying as far as the domain of this function goes, you can use all real numbers except we cannot use 8 and negative 8. So we're saying don't use these two numbers, but everything else is going to be okay. So I can use everything from negative infinity to negative 8. I can use everything in between these two numbers, negative 8 and positive 8. And I can use everything from positive 8 to infinity. So just like we did for solving our inequalities, you are going to write this in your interval notation. And you are not including the endpoints in this case because, you know, obviously they are making our numbers 0. So since there are two numbers we cannot use, you will see we came up with 3 interval notations or 3 intervals in our notation, however you want to look at that. So this is going to be your domain for this function over here. Question on this one, guys? So just remember, in this case, since you are not including the endpoints, everything will have parentheses on them. And that should be it. So you have a couple questions on this domain example here. Let's take a look at this guy. What numbers do you think this domain will not include? Okay, and Abdul Aziz, do you want to tell me how you came up with those numbers? Okay, so you're basically using factoring to simplify your denominator over here. So same process, take your denominator polynomial, set it equal to 0, and try and find what answers you can for x. So between x cubed and 9x, x will be a common factor. You can bring that guy outside. So that will leave us with x squared from the first term and minus 9 from the second term, right? Then you take each factor, set it equal to 0. So you will get x equals 0 from that first one, or x squared minus 9 equal to 0. So this one is already telling us that 0 cannot be our denominator. And you can see, you know, the moment we put 0 and 0 for our x values over here, you get 0 minus 0. So obviously we end up dividing by 0. With the second factor, x squared minus 9, just solve it either by factoring or square root property. And we will, of course, end up getting plus or minus square root of 9, which will come out to be x equals plus or minus 3. So 3 numbers that we cannot use in here. And I just want to show you, if you check with, -3 or +3, doesn't matter which one you use, you will notice that they will also give us zeros on the denominator. So let's take a look at this guy here. So that will give us 2 times -3 squared will be 9 minus 1. And then -3 cubed on the denominator will give us -27. -9 multiplied with -3 will give us +27. So as you can see, we'll end up with 9 times 2, which is 18. 18 minus 1 is 17. And then plus 27 minus 27 will end up giving us 0, which we know is going to be undefined. And the same thing will happen if you tried with +3 or 0 in this case. So now, when you are coming up with your interval notation over here, there are 3 numbers we cannot use, and that's 0, -3, and +3. So what do you think our interval notation will look like for the domain of this function here? Okay, let's see. Abdul Aziz, Oliver, you guys have -∞ to -3, -3 to 0, 0 to 3, and 3 to infinity. Yeah, so there are 3 numbers that we cannot use, which means we have 4 different intervals. So this guy over here will be -∞ to -3. This guy over here will go from -3 to 0. So very good. And then from here, you're going from 0 to 3. And then your last one will be from 3 to infinity, not including any of the endpoints. And then you are using union to combine all of them together. Alrighty, very nice. Good job, guys. So again, very quickly, we'll go ahead and type these guys in. And just be careful because you are typing, so many different symbols and numbers in here. So just be careful. There's one tiny error, and you know how my math lab is, it will not count your answer right. Okay, there we go. Now, these same places where we are not able to include these numbers in our domain are actually the same places where you will see the appearance of vertical asymptotes. So again, if you have seen the video lecture, you will be familiar with this.
I just got a quick question.
Sure.
So on that last example, could you just do the square root of 9, and that's how you figured out the numbers that you couldn't use right away without having to work that all out?
So you would still need to take the common x outside, because remember that gives you x equals 0.
Yeah.
Yes, you can do the square root of 9 to get the plus or minus 3.
Gotcha. And so if I had a 2 there, or I had a 4 there, I can just square root that. So then I come up with my 0, -2, and 2 right away without having to do all the work.
Right. Unless they change the bottom expression on you, and instead of x cubed minus 9x, if they gave you something like x cubed plus 4 or something like that, because I'm not sure what the different variations of this problem is. We can take a look by doing similar exercise. So yeah, it looks like they are giving you in a similar format, right?
Yeah.
So in this guy, then as you were saying, 0 of course would still be a number we couldn't use once you factored that out, and then plus and minus 2 would be the other 2 numbers.
Okay.
Yeah, very good. Alrighty, so as I was telling you, in the same location where your denominator becomes a 0 is the same location where you will see the existence of vertical asymptotes. Now, when we talk about asymptotes, keep in mind, these are imaginary lines. They're not actually part of your graph, but the behavior at the asymptote tells you that there's the existence of an asymptote there. So what happens is, if you look at this graph for the function 1 over x over here, you will see as this arm of our graph gets closer and closer to this y-axis, it actually starts heading upwards. Same thing's happening over here as we come from the left-hand side and get closer to the y-axis. This arm of our graph starts going downward. So what happens with these asymptotes is, so there's this vertical asymptote. Our graph is coming from the right-hand side. It gets really, really close to this line, but it will never touch the actual y-axis or the asymptote, and it's never going to cross it. So the idea is actually get really, really close to it, but it starts heading towards positive infinity if it's going up, and it starts heading towards negative infinity as it's going down. And that's exactly what's happening. As my x value is getting closer to 0, that y value is heading up to positive infinity from the right-hand side. And as my x is getting closer to 0 from the left, the y is getting closer to negative infinity. And you will notice that even if we put this in a table format, so you can see how our y values are getting closer and closer to 0. But since this is coming from the negative side, our y values are getting closer to negative infinity. From the positive side, the right-hand side, as our x values are getting closer to 0, our y values are heading towards infinity. So this is what happens with the vertical asymptote. Similar behavior happens with horizontal asymptotes also. So it's the same function, and you can see at the x-axis, we have a horizontal asymptote. The same thing, this arm of our graph is going to get really, really close to the x-axis, but never touch it, never cross it. And same thing with the left-hand side of our graph. This arm will get closer to the x-axis, but it won't touch, it won't cross either. And you can again see with this table that, you know, as our x values are actually heading towards infinity, the y value is getting closer to 0 because, you know, of course, this arm of our graph is going to get closer and closer to the x-axis. And same thing from the left-hand side, as your x is getting really large, your y is getting really small. So, you know, the y gets closer to 0, but the x gets closer to positive or negative infinity, depending on the direction from which you are coming from. So you can have vertical asymptote, you can have horizontal asymptote, you can also have oblique asymptotes. I don't know if I actually have a graph for an oblique asymptote here. I'll show it to you in your homework, but an oblique asymptote is basically the same thing as a slant asymptote. So we know horizontal lines will have a 0 slope. When we're talking about oblique asymptotes, we're basically saying those lines will have either a positive slope or a negative slope. So, you know, they will be a slanted line instead of just being horizontal. Another thing you should be aware of if you have seen the video lecture is that in a given function, you will either have a horizontal or an oblique. Both of them cannot show up in the same function. Vertical asymptote, yes. If you have x in the denominator, you will have a vertical asymptote, but horizontal or oblique, one or the other, not both of them, okay? So like in this example here, you know, they're talking about identifying all 3 of the asymptotes. So you will definitely have a vertical asymptote, but you will either have horizontal or oblique. You won't have both of them in there. So let's actually take a look at how we can identify some of these asymptotes. So we'll start out with this example. This is actually giving you the graph and asking you to come up with the domain and the asymptotes. So if you look at this guy over here, just in talking about the terms of the domain, looking at the x-axis, what do you think the domain for this function is going to be? And if you can't see this number over here where you have this dotted line, that's positive 3. Yeah, very nice. So remember, as I was telling you before, the place where you don't have your domain, the number you cannot use for your domain, is the same place where you have your vertical asymptote at. So yeah, very nice. Since you can see that dotted line represents our vertical asymptote, that means we can go from negative infinity to positive 3, and then we can go from positive 3 to infinity as long as we're just not including 3 in our answer. So yeah, very good. Nathan and Abdulaziz were looking from negative infinity to 3, union 3 to infinity. Now, when they talk about the equations for our asymptotes, let's take a look at the equation for the vertical asymptote. So vertical asymptote, of course, means the line is a vertical line. And remember, all vertical lines have the equation in the form x equals. So since my vertical asymptote here is at 3, we will say the equation is x equals 3. For horizontal asymptote, because that's a horizontal line, that means your equation is going to be in the form of y equals. And again, if you will see, for y equals, our horizontal asymptote is here at number 4. So of course, you would have the equation for the horizontal asymptote at y equals 4. Always write your horizontal asymptote, vertical asymptote, or even oblique asymptote as equations of lines. So they should always be in the format of, you know, x equals something or y equals something. Don't just write the numbers, you know, 3 and 4, because these are lines. So you have to write them as equations of lines and not just as numbers. All right, let's check our answer over here then. So domain, of course, is going from negative infinity to 3, not including that, and then union from 3 to infinity. So you will see when your asymptote question pops up, they're saying the asymptotes are x equals and y equals. So x equals will be for the vertical, so that's 3. Y equals is for horizontal, so that's 4. And there you go. Now, you know, of course, reading your asymptotes from the graph is not going to be as difficult, but, you know, reading it from an equation is definitely the part that we want to concentrate on. So let's take a look at this guy over here. And this is what I meant by an oblique asymptote. So you can see we no longer have a horizontal dotted line. We have that slanted line. So can you again tell me what the domain and the equations of these asymptotes are going to be? So just to identify this number here again, this guy is going to be negative 2. So what's the domain for this function? Pretty similar to the previous example, right? Except this time your vertical asymptote happens to be at the number negative 2. So yeah, very good. Let's see, we've got James with negative infinity to negative 2, negative 2 to infinity. Trey, same thing. Lowell, same thing. Now, Abdul Aziz, you were not including 0 also in yours. So if you take a look at this point here, you will see we are using x equals 0 at that point, right? So you still have a graph at x equals 0. It's only here at negative 2 that, you know, there's no portion of our graph which is going to be close to that -2. But for x equals 0, we definitely have this point over here. So that's why 0 is not going to be excluded from our domain. So just going from -infinity to -2, union -2 to infinity. Alrighty, very good. And then let's do our vertical asymptote. What is your equation for vertical asymptote going to be? And remember, you have to write these as x equals y equals. So what will your equation for the vertical asymptote be? Okay, so James, remember when you do y equals, that makes it a horizontal line, right? Let's see, I've got Abdul Aziz, Nathan, Shayna, very good, good job guys. Vertical line will be x equals -2. Now let's talk about how we can actually find the equation for our oblique asymptote. So that's this slanted line over here. So basically the idea is, how would you find the equation for any straight line? What's our process when we're trying to find the equation of a line that has a positive slope or a negative slope? And you know, we had kind of talked about this in chapter 1 also. You can use points on the line, very good. What else can we do? Yeah, choosing 2 points, definitely. Then what would you do once you found those 2 points? How would you move forward? Yeah, you want the equation in the y equals mx plus b format. Very good. So let's see, if we want our equation for the oblique asymptote in the y equals mx plus b, that means we need to know what the y-intercept is, and we need to know what the slope is. So looking at our line over here, what will be our y-intercept, and what do you think the slope of this line is going to be? So just look at that dotted line for the oblique asymptote and see where is it crossing the y-axis at, and you know, try and calculate that slope. Like you guys said, either you can choose points on the line, or you know, whatever process you have for coming up with your slope. So let's see, Nathan, you are saying slope will be 1, y-intercept is 0, and then Abdulaziz, you're saying the line should be y equals x. Alrighty, so let's take a look here. So yeah, you can definitely see that my line is crossing the y-axis, or in this case, even the x-axis at 0, 0. So that definitely makes our y-intercept at 0. And then as far as the slope goes, you know what you can do is you can definitely use 2 points on the line. And remember how we think about slope as rise over run? So if you think about it, we would have to go 1 unit up and then 1 unit right to get back on that line. So, you know, of course, that means you are going 1 unit up and 1 unit to the right. And since this is a line that is increasing from left to right, you know, our slope is definitely a positive slope. So yeah, just putting it all together, you would end up with y equals 1 times x plus 0, which will basically just come out to be y equals x. So y equals x is going to be your equation for the oblique asymptote, and then x equals -2 is for our vertical asymptote. So, and if this is something you need to review, then remember in chapter 1, you do have examples on this that you can go back and take a look at. Okay, so let's plug these answers in. Missed my infinity there. And then here again, you will see they're actually just giving it to you as x equals and y equals. So x equals is vertical, so that's -2. Y equals will be the oblique, so that's x. And there you go. So as I was saying, you know, from the graphs, it's still not that hard. But then when you are looking at the equation, you know, that's going to be the crucial one. You should be able to come up with your 3 different asymptotes from the equation. So let's start out with our vertical asymptote again. So take your denominator, set it equal to 0. Go ahead.
On that last question, when you have y equals x, at what situation will it be y equals -x?
Oh, if the line was going down in this direction.
Gotcha. Okay,
Right.
that makes sense.
Yeah, so when it's going up, it's positive slope. When it's going down, it would be negative slope.
Gotcha.
Alrighty, very good. So let me see what you guys come up with for the vertical asymptotes for this guy. So you are saying plus or minus, okay, should be -5 and +2. Okay, did anybody else get that answer or a different one? Same thing, Oliver, okay. James, you also got that. Shayna, you also got -5. +2, Nathan, same thing, Javier, Robert. Okay, very nice. So there's definitely a consensus on the vertical asymptote. So before I actually start writing on this, I did want to show you how to calculate your horizontal asymptotes. So again, the idea is it actually will depend on what type of a rational function you have. And based on that, you will be able to decide if your horizontal asymptote even exists or does not exist. So some of the information that you should be able to gather from your video lecture, you can look at the degree of the numerator and look at the degree of the denominator. And if the degree of the numerator is less than the degree of the denominator, then the x-axis will actually become your horizontal asymptote. In equation format, we write x-axis as y equals 0. If the degree of your numerator is equal to the degree of the denominator, then in this case, your x-axis is not going to be your horizontal asymptote. When the degree are actually the same between your numerator and denominator, that actually means it's going to be the ratio of your leading coefficients. So first of all, when I'm talking about the degree, we're talking about what is the largest exponent on your x variable. So you can see with this guy, on the numerator, I have x to the first power. On the denominator, I have x to the second power. So I would say the degree of the numerator is 1, the degree of the denominator is 2. So since the degree on my numerator is less than the degree on the denominator, you know, our x-axis is going to be the horizontal asymptote. So that's the y equals 0 line. When we are saying the degree is the same, in that case, you know, you could end up with something like, oh, I don't know, 2x squared over 5x squared, and you know, you could have whatever else after that. But in this case, since both I have x squares on both my numerator and denominator, for this guy, your horizontal asymptote would actually be at the ratio of our leading coefficient. So that would become 2 over 5. So it's definitely not, you know, going to be the x-axis, but it's going to be the ratio of these numbers. Similarly, if you had another function which was, I don't know, negative 3x plus 7 divided by 4x, I don't know, minus 2, which let's not make it a 2 since that can be factored out. Let's just make it 1. So again, since my degree is the same, the ratio of our leading coefficients would end up becoming negative 3/4. So that's what happens when the degree is equal. So these are the conditions in which you can get horizontal asymptotes. Now you can also have expressions which would end up looking something like this, where you actually just have a number on the top and your x variable is going to be on the bottom. It can show up just as x, or they can be x squared or x cubed. So, you know, any form of that. This example that we are looking at here right now is of the same format. You have number 1 on the top and then x squared and something else on the bottom. So they all fall under this same format. So what happens in this case? You know, when we're talking about horizontal asymptotes, we're basically saying what is your function doing as the x is going towards positive infinity or negative infinity. So where is your function headed? So these are actually like limits that we were talking with our leading coefficient test in the previous section. So what happens in this case, you will see we take actually the highest degree of our polynomial, which in this case happens to be that x or x. So we take each term of our rational function, numerator and denominator, and divide it by these x values. You know, whatever is the highest degree of x in your rational function. So some of these will end up simplifying, some of these will end up staying as it is. So if you think about this, when your x is headed towards infinity, so x is getting really, really large, but your numerator will just stay at number 2 or at number 3, right? Because those guys are not changing. So as x is going to positive infinity or even negative infinity, your entire fraction is actually headed towards 0. Just try plugging these into your calculators. You can try 2 divided by 1,000, 2 divided by 10,000, and, you know, keep increasing that number on the denominator, and you will see these guys are getting closer and closer to 0. So as x gets really large, your numerator actually is not growing. So the denominator is becoming really big, but the whole fraction is becoming really small. So for all these types of examples, this is the same thing where the degree of your numerator is smaller than the degree of your denominator. And that's why your x-axis is going to be the horizontal asymptote. The only instance where you end up with an oblique asymptote is in this case where the degree of your numerator is larger than the degree of your denominator, at least by 1 degree. So if the degree of your numerator is going to be larger than the degree of the denominator, you have an oblique asymptote. And there's a really nice table or box over here which summarizes this. So you will see this guy is talking about for the vertical asymptote, take your denominator, set it equal to 0. For horizontal asymptotes, if the degree of the numerator is less than the degree of the denominator, your x-axis or y equals 0 is going to be the horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, then your horizontal asymptote is going to be the ratio of the leading coefficients. And then for the oblique, the degree of your numerator has to be greater than the degree of the denominator. And in that case, our oblique asymptote is going to be y equal to the quotient. And we'll talk about this here in a minute. So the idea is they're actually asking you to rewrite the function as quotient with added with the remainder over divisor. But honestly, you don't have to worry about that as long as you remember that your oblique asymptote is going to be equal to the quotient when you perform your little division between these polynomial functions. So let's take a look at that over here. So in this case, the degree of our numerator is actually going to be degree 0 because you just have the number 1 there. There's no x variable. So that's assumed as x is to the 0 power. So that means you have degree 0 on the numerator, degree 2 on the denominator. So this definitely tells us our horizontal asymptote is going to be at the x-axis, which is the equation y equals 0. So we know that's going to be this option over here, which actually these guys are only asking for vertical asymptotes. So this one will be for the next one. For vertical asymptotes, you guys had -5 and +2. So you're taking that denominator polynomial, setting it equal to 0. This guy factors into x minus 5, x plus 2, but you guys were actually giving me x equals -5 and x equals +2. Because when I multiply -5 with +2, I get -10. When I add -5 with +2, I get -3. Yeah, so actually your signs were reversed from what you gave me. Yeah, it's okay. So when you take each one of these factors and set it equal to 0, you will get x equals +5 and x equals -2. And I'm kind of glad that this happened. So you can kind of see something that may seem obvious to us by looking at the polynomial may not be the same answer that you should end up coming up with. So that means you're looking at x equals, let's see, +5 and x equals -2. And then, you know, of course, we have y equals 0 for our horizontal. So let's check these answers very quickly here. So 2, -2, and +5 for the vertical asymptotes. And then they should actually give you a second option for the horizontal. Yeah, so now you can see for horizontal asymptote, that would be y equals 0. So just kind of carefully with that. Let's take a look at this guy. And this one you should actually see that we have larger degree on the numerator, smaller degree on the denominator. So this is an example of where we should have an oblique asymptote. And then, you know, definitely we would have a vertical asymptote. So can you tell me what our vertical asymptote is going to be for this rational function? Very nice. Yeah, so that's taking our denominator and setting it equal to 0. Again, guys, -3 is not an answer. It should be an equation. That's your x equals -3, which will, of course, go into this first box here. Then for our second one, we will need to use division. Now here, for the oblique asymptotes, you can use long division. So again, let me kind of refresh in. That's why I was kind of insisting earlier that, you know, at least get a brief working knowledge of how a long division works. So again, let me walk you through with this long division here. So we're taking x plus 3, dividing it into -x squared plus 2x. So since this guy has a negative, we should have a negative in our quotient. Since we only have an x term over here, we're going to need an x term in our quotient. So you will have negative x in the quotient. And then remember how I had told you, you will take that negative x from our quotient and multiply it with our divisor, x plus 3. So when we distribute this guy, we end up getting negative x squared, negative 3x. And then with long division, we always end up subtracting at this point. So negative times negative will make this guy into a positive. Negative times negative will make this guy into a positive also. Negative x squared, positive x squared will cancel out, leaving us behind with 2x plus 3x will of course add up to 5x. And that means in our quotient, we should have a positive 5. So we're taking that positive 5 and again multiplying it with our divisor. 5 times x is 5x. 5 times 3 is 15. Again, we'll end up subtracting this. So that means we will have negative 5x here, negative 15 here, positive 5x, negative 5x will cancel out. And we'll get a remainder of negative 15. So when they're saying you can rewrite your function as quotient plus the remainder divided by the divisor, this is what they're talking about. So instead of leaving it as negative x squared plus 2x divided by x plus 3, you can actually rewrite it in this format. But unless they ask you to, you don't have to write it like this. We're only interested in the oblique asymptote, and our oblique asymptote actually comes from the quotient. So our quotient here is negative x plus 5, and that's what we need for our oblique asymptote. So it's always going to be y equals whatever quotient you get from performing this division. So we'll go ahead and type that in. So negative x plus 5, and then we can go ahead and check our answer. And there you go. So long division is definitely one of the things you can use. With this particular type of example, you do have the option of using synthetic division, but that will not be possible for all of these examples. And I'll show you which ones synthetic division is not recommended. So you take your denominator, set it equal to 0. So that will end up giving us x equals negative 3. So we are dividing this by negative 3. The coefficients from our polynomial on the top are going to be negative 1, positive 2. And since we don't have a constant term, you will need to put a plus 0 in there to hold the space for the constant term. And of course, you saw we didn't have to do that with the long division because it automatically created a space for it. But with synthetic division, we will need to put the 0 in there. So again, bring down that negative 1. Negative 1 times negative 3 is positive 3. That adds up to a 5. 5 times negative 3 is 15. And again, you will see we have the same remainder. And we'll get the quotient from here. So our original polynomial was square. So this will be just a 1-degree polynomial. So minus x plus 5. And that will become our oblique asymptote. Which is of course what we had over here. So like I said, this particular example, you can definitely use synthetic division, but let me show you the example where synthetic division is not advisable. Okay. So while I'm making my way to that example, do you have any idea what your, if you will have oblique or horizontal asymptote here? Remember, only when the degree on the numerator is larger then the degree in the denominator, you get oblique. And in this case, -10 is a degree smaller than the x, so you will have horizontal, and actually it's going to be at the x axis in this case. Same thing, this is actually very similar to the example we did 2 examples ago. So 1 over x squared minus 25, you will again only have a horizontal asymptote in this case. This one here, you can see how the degree is same in the numerator and denominator. So this is where this rule 3 kicks in, that you take the ratio of your leading coefficients. So that's kind of what you are going to use here. So all of these were examples of, having horizontal asymptote. Now this one is definitely an example for oblique, and you can see they're asking us to find the oblique. Now look at the denominator here. You're only given the variable x. There's no plus or minus, number being added. So when I set this equal to 0, that means if you were going to use synthetic division, you would have to divide by 0. And that's the reason why, for this example, I do not recommend using synthetic division. And this is actually not that hard to solve by using long division. You are dividing by x. We have x squared plus 7. So since we're missing that middle term, you can put 0x for that missing term over here. So when you do your long division, I only have x in my divisor, so I will need an x in my quotient. X times x will give us x squared. And then, like I said, with division, we always end up subtracting these. So positive x squared, negative x squared will cancel out. This guy is just 0x, so obviously you don't have to bring him down. So the only number that comes down is the 7. So 7 is your remainder. X is your quotient. So our oblique asymptote will actually just be y equals x, and you're done. So, it's not too bad of a long division. As long as you have x plus 2, x minus 3 on the denominator, use synthetic division if you're more comfortable with that. But when you see just x on the bottom, use long division. So let's go ahead, plug this guy in. So this guy here will just be x. And then they're actually going to have you select your graph for this one. Let's clear this out. Our oblique asymptote is y equals x. So which graph do you think we can choose? Which of them might work and which one will not work if your oblique asymptote is y equals x? And you can kind of see where your vertical asymptote would also be at. Yeah, exactly, because your y equals x line is basically a line with a positive slope. So we know that line has to be going upward. So very nice. It will be a graph between A or B, but we know for sure C and D are not going to work because both of these graphs have a negative slope on that oblique asymptote. So we know those graphs are definitely not going to work in this case. So C and D are out. And then between A and B, which ones do you think, which one of those two? If it will let me expand the graph. There we go. So out of A and B, which one do you think will satisfy our example over here? X squared plus 7 over x. If you had to pick one, which would you guess? Okay, you know, you're guessing B. So looks like a bunch of you are going with B. James, you also had B. Nathan, Abdulaziz, Oliver, Robert. So what's kind of making you choose B in this case? What's your reasoning? Abdulaziz, you're doing that because of the x squared, so you're kind of going for that parabola S shape. What about the rest of you? What made you choose B? Okay, Shayna, same as Abdulaziz. James, you're talking about the +7 that we had. The +7 that we had over here. So let's take a look at graph B over here. Let's make him bigger. So the +7, technically, that means that it's making your graph move up by 7 units. But, you know, obviously you will say it's moving up. I'm not entirely sure if it's moving up by 7 because that would be 3, 6, 7 would have to be, I think, somewhere over here. But I actually like Abdul Aziz's explanation in this case. Okay, Nathan, you're saying the graphs have always seemed to be on the inside of the narrow split between the asymptotes. Yeah, and you do actually notice that pattern. But so like Abdul Aziz said, you know, because you have that x square, and we know x squares give you parabolas, and in this case, this is not obviously a parabola, but it still has a similar kind of shape to it. But when you look at the graph A, you know, obviously we're not really seeing a whole lot of that parabolic shape in this case. So yeah, graph B is a good choice. And then, you know, we can check our answer and see if that's okay or not. And obviously it is. So just remember, this would be the type of example where my recommendation is to use long division instead of synthetic division. Now, this is what I was talking about in terms of limits earlier, just like we did with our leading coefficient test. So they're asking you what's going to happen as x goes to positive infinity. Where is our function expression headed? And in this case, because your x is in the denominator and this x is heading towards infinity, that means your entire fraction, like I showed you in your handout, will be heading towards 0. So you will actually have 0 as your answer over here. So this is the same kind of format that you saw with your leading coefficient test in the previous section, but you know, there we were using polynomial functions. So our answers were normally heading to positive or negative infinity. In this case, our function is a rational function. And that's why, because your x is in the denominator and you have a constant number 3 on the numerator, this guy is heading towards 0. So you would, you know, of course, have 0 as your answer in here. All righty. So just your horizontal, vertical, oblique asymptotes, how to find the domain for these functions. And this guy, again, I will let you work on this. They're asking you to put it in the lowest forms and then come up with your domain. And I think they'll ask you about asymptotes in that case. But what I wanted to look at was how we can actually use the graphical method, or also you actually have the test point method to help you solve these rational inequalities. So basically the idea is, if you wanted to use graph, you would have to find out where your asymptotes are, you know, draw them as dashed lines. Since they're imaginary lines, if you can check for symmetry to see if it's an odd or even function, find your x and y intercepts, and then, you know, of course, come up with the shape of your graph by using more points. You can do that, or you can always use the test point method, which is what we had kind of talked about in the last example. So if you wanted, sorry, in the last section. If you wanted to use the test point method, make sure all your expression terms are on one side and you have 0 on the other side. So your polynomial, your rational function with the polynomial should be on one side, 0 on the other. You take your numerator and your denominator, set it equal to 0 so that you can find all the zeros for your polynomial. And then we will actually need to then use test points from each one of those intervals and come up with what our sign is going to be, positive or negative. Now they are talking about the rational function will be undefined for the zeros of the denominator, because remember that's where we have our vertical asymptotes. And they're saying, okay, so yeah, locate the zeros, get your test point. So let's take a look at this. Now, if you wanted to use the graphical method as they're asking you, you will need to come up with what your vertical asymptote is, this guy will have a horizontal asymptote, where that's going to be at. And then, of course, you can kind of come up with a rough sketch for this function. So looking at this, 1 over x squared plus 25, do you know where your vertical asymptote is going to be at? At what number? James, you're saying plus or minus 5. Abdulaziz, you're saying no vertical asymptote, okay? Let's take a look. If I take my denominator, set it equal to 0, you would actually end up with negative 25. So x squared equals negative 25. And once you do your square root property, what do you notice over here? You're taking the square root of a negative number, aren't you, on the right-hand side? Yeah, exactly. You've got imaginary numbers because once you simplify this, you will have plus or minus 5i. You cannot have imaginary numbers because our graph is based on the real number system. So that's why we actually have no vertical asymptotes here. For your horizontal asymptote, you can see the degree of our numerator is smaller than the degree of our denominator. So we know that means our horizontal asymptote is going to be at the x-axis at the line y equals 0. So we can draw that. Whoa, didn't mean to do that. We can draw that as our dotted line or dashed line for the asymptote. Now, if you actually look at the graph for this function, and let me show you that with Desmos here. You will actually end up with 1 divided by x squared plus 25. And I know I've got this whole mishmash in here, but if you zoom out, it actually just ends up looking like a horizontal line. But when you zoom in, you will actually see there's a little bit of a bigger gap right in the middle of the graph where the origin is. But then as you move out, those edges actually start getting narrower. Now, if you wanted to find out where your intercepts are, you can take the function and set the entire function equal to 0 to help you find the x-intercept. We make the y value 0, so you would end up getting 1 over x squared plus 25 equal to 0, which would actually, to get rid of the denominator, we would need to multiply both sides of our equation by this denominator. They would cancel out here, but on the right-hand side, you're multiplying them with 0. So you would actually end up with a 0, so that means we have no x-intercept, And we saw that in our graph on Desmos. To find the y-intercept, we would obviously make our x value 0. So that means you would have y equals 1 over 0 squared plus 25, which would give you 1 over 25. So you can see that's going to be a pretty small number, 0.04. So right, a little bit above the origin 0, 0. So your graph actually has this shape where it's narrowing as it goes out to positive or negative infinity. So it's, and this is an exaggerated shape, but it's kind of like this. Obviously, you're not seeing that big of a hump on your function over here, but that's basically what this function will come out to be. So a very interesting graph compared to what we have seen so far. No vertical asymptote, you only have a horizontal asymptote, no x-intercept, a really tiny value for your y-intercept. So when you try and look at this function, or you can look at the graph here in Desmos, over which interval do you think our inequality will be satisfied? So what will be your solution set for this guy? Yeah, I mean, after all that trouble you went through, you're basically, you can see over the entire domain, this function is going to be, having a value of y greater than 0. So that's why I'm not a big fan of a graphical method, because sometimes your graphs just come out looking so unexpected than what we would imagine. I honestly prefer the test point method over these guys. But, it's kind of good to know you do have the option. If you do have a nice graph to work with, you can definitely do that. But yeah, test point method works out a lot quicker. Don't have to mess around with the graphs. And I think they give you a nice conclusive answer. So with this guy, you should notice our vertical asymptote is going to be at, when you simplify this, x equals -6. If you talk about the horizontal asymptote, you will see if we look at the degree of our x terms here, it's the same degree. So remember, when it's the same degree, you take the ratio of the leading coefficients. So that will end up becoming 1 over 1, which, of course, tells you your horizontal asymptote is going to be at y equals 1. Now let me show you what happens when you try to find your zeros. So remember what they told us here. For the test point method, find the zeros of your denominator and the numerator. So that's the part we are going to be looking at. You take your expression on the top, set it equal to 0. Take the expression on the bottom, set it equal to 0, and you will end up getting x equals -1, x equals -6. This number obviously is the same as our vertical asymptote, right? Your x minus 1 actually is your x-intercept, where your graph will be crossing the x-axis at. But again, we're not worried about the graph. With the test point method, you take these two numbers, put it on your number line, and then from each interval, we will be selecting a test point. So anything smaller than -6, you can use whatever number you want, but we'll just keep it simple. We'll do -7 as our test point here. Between -6 and -1, you can again use whatever you want, but I guess I'm going to go with -3. Between -1 and infinity, you know what? I think I'm going to use 0. That'd be a nice number to use. Now, we've got our zeros from the numerator and denominator, -1, -6. We got our test points from each interval. Now we have to test these test points and see which section will give us a positive answer, which will give us a negative answer. So let's do a little math now. So let's check these for our test points. We'll start with the one on the left. So x equals -7. So in our function, that will be -7 plus 1 over -7 plus 6. What kind of answer will you get when you simplify this? Yeah, it's going to give you a +6. Very nice, because we will get -6 on the numerator, -1 on the denominator. So that gives us a +6. And that means all our y values are going to be positive in this interval. Obviously, repeat the process with the other number. So now our next test point was -3. So let's see, that would be -3 plus 1 divided by -3 plus 6. And what does this end up giving us? -1/2. Okay, so did I do my calculation incorrect? Because -3 plus 1 will give us -2. -3 plus 6, wouldn't that give you +3? Yeah. So why did you guys come up with -1/2? Unless you did 4 on the bottom instead of 3. So -2/3, which of course then tells us all this y values in the middle are going to be negatives. And then let's check for the last one, which was a test point of 0. So that's 0 plus 1, 0 plus 6. And 0 really does make our life a lot easier, because you end up with +1/6. So obviously every y value here is going to be positive. Now look at your interval, look at the number line, and what do you think your solution set is going to end up looking like? Okay, so let's take a look. Abdul Aziz, you've got -∞ to -6. That's right, because our inequality is greater than equal to 0. So that's going to be this section here, where we have a positive y value, and then you're going from -1 to infinity, which is this section over here, where again your y value is positive. Now you are including -6 and -1. Is anybody noticing a problem with that? Can we include both -6 and -1? Yeah, remember at -6, you have your vertical asymptote. So obviously, we cannot include -6 in our answer set. So that's why you have to use parentheses and not brackets. And it's a very tiny little thing, but you have to be extremely careful about that. So include the -1, but do not include the -6. So be very careful, because these are rational functions. They behave a little bit differently than what we have seen with our other functions here. So -∞ to -6 union, including -1 to +∞. Okay, so let's check this guy. Okay, so this saying, start by determining when the rational expression on the left is positive or 0. So what do you think we need to change here? Where is our function greater than and equal to 0? Did we go wrong with our math over here? I didn't think we did. -6, -1 is +6, -2, +3, +1, +6. So yeah, you've got positives in those intervals. We cannot include -6 because that's the vertical asymptote. -6. But if you go from -6 to infinity, you're going from here, which would of course include the negative portion also. So we know that's not possible. Did I forget a comma? Oh,
Yeah, in the first, good catch, Oliver.
yeah, I just saw that. Thank
I
you.
almost didn't see it.
Yeah, me neither. Wow. Okay, keeping my fingers crossed. There we go. Man, one pesky little comma. And I had to go check my whole math, but that's what my math lab does to us, like, likes to torture us. All right, guys, so this was the last part of our section 3.5. So basically you can see this section, we're really concentrating on domain for these functions, finding all 3 different types of asymptotes, and then at the last part, looking at how you can solve your inequalities. So let me know if you have any questions. So on Monday afternoon, we'll be taking our chapter 3 exam. And then a week from today, next Wednesday, we'll get started with chapter 4. Okay. So I'll be here today. I'll be here tomorrow. I have office hours tomorrow. If you need help, please let me know. All right, everybody, have a wonderful weekend. Stay safe, and I will see you on Monday afternoon. Take care, guys. Bye. Thank you. Yeah.